All right. So today we're going to deal with a device called a capacitor. There are three very popular devices in electronics. They are the resistor, the capacitor, and the inductor. So today we're going to look at a capacitor, and in later chapters we're going to look at resistors and dielectrics. Okay, so let's start by defining what a capacitor is. A capacitor is basically two conductors separated by an insulator. A capacitor is simply two conductors separated by insulators. It could be two or more, but we're going to deal only with two in this chapter. So you can say this is two conductors separated by an insulator. Separated by an insulator. And what is it for? It's used to store charges or electrical energy. It's used to store charges or electrical energy. To store charges or electrical energy. Electrical energy. Okay, so let me start by giving you the circle symbol of capacitors. The circle symbol is as follows. Circle symbol is basically two parallel lines. The symbol for capacitor is two parallel lines connect like this. Okay, if one of the lines is shorter, it's a symbol for battery. But if the two lines are the same length like this, it is a capacitor. All right. Now, suppose we have this capacitor over here. Let's see how it's used to store charges. And then you connect it to a potential difference, maybe a battery. This is a battery. The long one is a positive terminal, the short one is a negative terminal, okay? So what this battery going to do is going to take charges from this conductor over here, okay? This positive terminal is going to take electrons from this plate. So we're going to have deficiency of electrons this side, and then we'll take the electrons the other side, then you'll have charges over here, okay? And then if you break the circuit, what do you have? You have two conductors with charges in them, okay? They have nowhere to go. They have nowhere to go. They get stored in the capacitor, okay? That's why we say it's used to store charges. You charge it, you break the circuit, and the charges remain over there. So that way you can use it to store charges, all right? So let's say the potential difference of this battery is delta V, okay? And then this delta V makes this capacitor to store a charge Q over here, okay? So Q stands for the charge accumulated on the capacitor. Of course, delta V is potential difference, okay? Now, experiment shows that the charge accumulated by the capacitor is directly proportional to the potential difference. The greater the potential difference of the battery, the greater the amount of charge you get on the capacitor, okay? So from experiment, we have the following. The charge is proportional to the potential difference, okay? So what does that mean? The ratio between the charge and the potential difference across the capacitor is a constant, okay? This constant is a property of the capacitor, and it's called the capacitance of the capacitor. So we're going to use C to represent it, and it's called the capacitance of the capacitor, okay? Capacitance of the capacitor. So we have the following question. Q over delta V equals C, but it's most of the time written as Q equals capacitance times potential difference. So you've got this, which is a defining equation of a capacitor, okay? Q stands for the charge accumulated in the capacitor. Delta V is a potential difference between the two conductors of the capacitor, and C is a property of the capacitor itself that we call capacitance, okay? Now, why do we say it stores energy? Let's say you have this capacitors, these two conductors carrying charge over here, okay? What happens if you connect this by a conducting wire, okay? These electrons are going to go over here. So you're getting kinetic energy out of it, okay? Since you're getting energy out of this, we say that there is energy stored by these two conductors, okay? So that's why you say a capacitor is used to store energy. If you connect these two by means of wire, you get motion, kinetic energy. And that kinetic energy is coming out of the energy stored by the capacitor, okay? Now, we're going to look at different types of capacitors. We're going to start with the most common one called the parallel plate capacitor. Parallel plate capacitor. That is where a capacitor is made between, where the two conductors are plates, parallel plates, okay? So you've got something like this. These two conductors parallel to each other is called a parallel plate capacitor, okay? So our goal is, as I've said before, the capacitance is a property or of the geometry of the capacitor, okay? So we're going to get a formula for the capacitance of a capacitor, all right? So suppose we have two power plate capacitor. Let me just align for the power plate capacitor, okay? And we want to get an expression for the capacitance. Let's call C parallel. That one is charge divided by potential difference, right? Now the potential difference, if you remember, is electric field times distance. There is electric field inside over here. This is electric field inside over here. If you remember from the last experiment, the electric field inside is uniform and the electric outside is approximately zero. There is no field over here. There's only field inside, if you remember the experiment from last time, okay? So we have a uniform electric field inside and we have approximately zero electric field outside. And the potential difference is electric field times distance, where this is the separation between the two plates, the distance, all right? Now, how do you get the electric field? Well, what we can do is we can use Gauss law. If I take this small area over here, like this, let's say this area is dA over here, all right? So the flux you see over here is over here outside, the electric is zero, so you don't get any contribution from here. And on this curved sides over here inside, you don't get zero because the area and the electric field are perpendicular to each other, okay? You get contribution only from this one over here. So the flux will simply be E times dA, okay? And then that equals K, 4 pi K times 4 pi times the charge enclosed. The charge is in here, okay? So this area is dA. If the charge density is sigma, then this charge enclosed inside is sigma times this small area element dA over here, okay? So you see this dA cancels out. You get the electric field is 4 pi K. You remember 4 pi K is simply 1 over epsilon, okay? Epsilon is defined to be 1 over 4 pi K. And then okay, this has gone away. What does the charge density equal to? If the uniform charge density, if Q is the total charge, you divide by the area of the plate. That's what this one is, okay? So this one is total charge divided by the total area of the plate, okay? So we have this equals Q over area, okay? So the electric field is simply the charge over area and then divided by epsilon, all right? So now let's go to the capacitance. The capacitance is, of the power plate capacitor, is the charge divided by the potential difference, okay? So that is the charge divided by the electric field times distance, the electric field times distance, right? The potential difference electric times distance. So let's put this over here now. So we've got Q, and then the electric field is this one, 1 over epsilon charge divided by area. That's the electric field, okay? And then of course we have D over here. I just replaced it E by this one, okay? So this is happening. The charge goes away. The epsilon A go up, epsilon A divided by D, okay? So you got a formula for the capacitance of the capacitor in terms of its geometry, in terms of the area of the plates and the separation between the plates, okay? So we have a formula for the capacitance of a parallel plate capacitor. You get C parallel equals epsilon A is the area of the plates and D is the separation between the plates, okay? So you see, it just depends on the geometry of the capacitor, all right? So epsilon, if you remember, is 1 over 4 pi K, okay? So it's about 8.85 times 10 to the power of negative 12 in SI units. A is the area of the plates, okay? And D is separation between the plates. This is separation between the plates. Now we're assuming the insulator inside is air or vacuum, okay? Later we're going to modify it for an arbitrary insulator, which we call a dielectric, Okay, so that's the formula for the capacitance of a parallel plate capacitor. It's proportional to the area of the plates and inversely proportional to the separation between the plates. Okay, and then next we're going to look at cylindrical capacitor. Cylindrical capacitor. This is a capacitor where the two conductors are cylinders. Okay, so let's say this is the inner cylinder. Okay, this is the inner cylinder. Let's say its radius is A, and then we have another cylinder over here, like this. Let's say the radius of this one is B. Okay, so we have two conductors, two cylinders, one inside, one outside. That's so that forms the cylindrical capacitor. A capacitor is simply two conductors separated by an insulator. We just have two conductors of cylindrical shape. That's why we're calling it cylindrical capacitor. Okay, so again, the capacitance is the ratio between the charge and and the potential difference. All right. So this is our formula for capacitance is charge divided by the potential difference. Okay. So suppose we have, let's say this is the positively charged one over here, and then this is a negatively charged conductor over here. Okay. So we have to get an expression for the potential difference. Now we have an electric field that's not constant. Okay. You can use Gauss law to find the electric field. Remember, you can take Gaussian surface over here. We already did it. The electric field is something like this. E equals 2k lambda divided by r perpendicular, or in the direction of a unit vector parallel to the axis. This is the electric field we got for a cylindrical charge. I mean, well, we did it for a line charge, but it's just like a line charge. The charge density now is a total charge in the cylinder divided by its length. Lambda is a linear charge density. Okay, so now we have to do the potential difference. The formula for potential difference, if you remember, is this one. Delta V is the negative of the dot product between and the path element over here, like this. This is the definition of electric field. Okay, now electric field is a conservative force, so we can choose any path we want. So we can do the integral in this direction over here. Okay, so we take a small element over here. This element over here is a path element perpendicular to the axis of the cylinder. Okay, so this path element over here, this path element over here, we can say is dr perpendicular in the direction of the unit vector perpendicular to the axis of the cylinder. Okay, so now let's do this dot product. E dot dr would be the electric field is 2k charge density divided by r perpendicular in the direction of er perpendicular. Okay, dotted with the path element is dr perpendicular in the direction of perpendicular to the axis, and then er perpendicular. Okay, so these are two identical unit vectors. When you dot them, you just get one. Okay, so this one over here, e d, the dot product of the electric field and the path element is simply 2k lambda r perpendicular, and we just have dr perpendicular. Okay, so that's the integral we have to do. So the potential difference is a negative of the the integral of this dot product, which is 2k lambda r perpendicular dr perpendicular. And from where to where does this integral go? Okay, we're looking at the potential difference between this surface and the surface over here. The radius of this one is A, the radius of this one is B. So this integral goes from A to B, okay? All right, so now we just do this integral. You see, well, 2k lambda is a constant, and then you've got, well, the integral of dr perpendicular over r perpendicular going from A to B. All right, what is the integral of 1 r perpendicular? What's the integral of 1 over x?
Log natural.
ln x, yeah. So this one is going to be negative 2k lambda ln r perpendicular going from A to B, okay? So that's negative 2k lambda ln of B minus ln of A is ln of B over A, okay? So that is the potential difference, but we're not interested in the sign. So let me just put absolute value. So if I just say absolute value of potential difference over here will be 2k lambda, and then ln b over a, okay? So this is the potential difference over here. But remember, the charge density is the total charge divided by the length. This is linear charge density, okay? So with that, we have 2k, this charge density over here is the total charge divided by the length, and then you've got ln b over a. So remember, a and b are just the radiuses of the two cylinders, all right? Now we go to the formula for capacitance. This is charge divided by potential difference. Okay, so charge divided by this potential difference over here. So you've got 2k charge over L, and then you've got ln B over A. Okay, so this is that this charge goes away and this L goes up. So you get this formula for the capacitance. We have L over 2k and then ln B over A. Okay, so you see the capacitance is simply a function of the geometry of the capacitor. L is the length of the capacitor, A and B are the radiuses of the inner cylinder and the outer cylinder. Okay, so you see the capacitance of the cylinder just depends on the geometry of the capacitor. Okay, next we're going to look at spherical capacitor. That is a case where the two conductors are concentric spheres, okay? Spherical capacitor. So in this case, we're gonna have an inner sphere, let's say of radius A, and then we have an outer concentric sphere of radius B, okay? So let's say this is our positive charged plate over here, and let's say this is our negatively charged plate over here, okay? So because of this, we're gonna have field inside. Okay, for the field, if you want to find the value of the field over here, you can use a Gaussian surface to do it, but we have already done it, so I'll just give you the formula for the electric field. It looks like the electric field due to a point charge. The electric field will be like this. It is K, the total charge inside, over R squared in the direction of the unit vector, okay? So if you take an arbitrary point over here, the electric field over here is radial, is in the direction of the position vector, and is charge divided by the square of the distance is inversely proportional to the square of the distance. We have already done it when we were doing Gauss law, so let me just write the formula over here, okay? So we can choose any path to do the integral for the potential difference, okay? The potential difference is this one. Potential difference is the negative of the dot product between electric field and a path element, okay? So I'm going to do the integral in the radial direction like this, okay? So if I take a small path element over here, that path element is simply dr in the direction of the unit vector, okay? So my dr is simply dr, the change in the radius, in the direction of the unit vector. Okay, now let's do the dot product between the electric field and the path element. This one, kq over r squared in the direction of the unit vector, dotted with my path element is dr in the radial direction in the direction of the unit vector. Okay, so I've got a dot product between two unit vectors, which is going to be 1, right? So this one is simply kq over r squared dr. That is the value for E dot dr for this part over here. And then to get the total, we just integrate. And that goes from A over here to B over here. We're trying to get the potential difference between the inner conductor and the outer conductor, all right? So the potential difference is the negative of this integral, kq over r squared dr, okay? So this is negative, well, it goes from A to B, the inner radius to the outer radius, okay? So we can take the constants out, kq, and then, well, this is dr over r squared. As you know, that's going to be negative 1 over r, right? The integral of 1 over r squared is negative 1 over r. So this will go away. So you've got kq, and then 1 over r going from A to B, okay? So we get kq that is 1 over B minus 1 over A. Okay, so you get KQ, and then of course this will be A minus B over AB. Okay, so as you can see, this is negative because A is smaller. Okay, but we just simply take the absolute value. We're not interested in the sign, so I'll put this in absolute value and reverse this, put B in front. Okay, so the potential difference is this one, KQ, and then you have B minus A over AB, where A and B are the radiuses of the inner conductor of the capacitor and the outer spherical conductor of the outer spherical conductor. All right, there's a potential difference. Now let's go to the definition of capacitance. Capacitance is charge divided by potential difference, right? So our capacitance is going to be the charge divided by KQ, and then you've got B minus A over AB. Okay, you see the charge cancels out, so you get the following formula for the capacitor. AB goes up, and then you've got K times B minus A. So you see, if you've got a spherical capacitor, if you know the radiuses of the two capacitors, you can calculate the capacitance of the capacitor very easily using this formula. Okay, so as you've seen in all cases, the capacitance is simply a function of the geometry of the conductors, the radius, the lengths, the area, and so on. Okay, so these are the three types of capacitors we have. But the most popular one that they use in electronics is the parallel plate capacitor. Okay, they just have two parallel conductors separated by an insulator. Okay, so next we're going to look at combinations of capacitors. Combinations of capacitors. Now, there are two kinds of combinations. They're called parallel combination and series combination, okay? So we're going to start with parallel combination. Parallel combination is branched combination. Branched combination, okay? Something like this. Let's say I have these capacitors over here. If they're connected like this, it's said to be a parallel combination, okay? So that's what I mean by a branched combination. A combination look like this. That's a branched combination is what we call a parallel combination, okay? Now we want to look at the property of this kind of combination. Our goal is to get an expression for the single capacitor that can replace this combination without changing anything outside, okay? We call it equivalent capacitance, okay? So let me define what I mean by equivalent capacitance. Equivalent capacitance of a combination, equivalent capacitance of a combination is the single capacitor that can replace the capacitors without changing anything outside, okay? This is a capacitor that can replace the combination, a capacitor that can replace the combination without changing anything outside. Combination without changing anything outside, okay? Anything outside. The charge, the currents of the ore remains same, anything outside the combination. All right, so how do you define it? If you've got a single capacitor, then its capacitance should be the total charge divided by total potential difference. So that's the definition of CEQ, equivalent capacitance. You take the total charge, you divide by the total potential difference across the combination, okay? This is a definition of equivalent capacitance. Q stands for total charge across the combination, and this one represents this total potential difference across the combination. So that's our goal in this section. We want to find an expression for the single capacitor that can replace the combination without changing anything outside. Okay. All right. So working on a parallel. Suppose let's say we have this battery connected to the following parallel combination. Let's say we have this situation over here. We have three capacitors connected in parallel like this. Okay. Now suppose the total potential difference is delta V, and these are C1, C2, and C3. Okay. Now let's look at the properties of this kind of combination. First, let's look at the potential difference. Okay. You see, these wires are conducting wires. Okay. So there isn't any potential difference across a conducting wire. All these points in these wires are the same potential. Okay, you remember we talked about conductors in electrostatic equilibrium later in the previous section. So all these points are the same potential. All these points are the same potential. What that means is this potential difference over here is the same with this potential difference over here, this potential difference over here, and this potential difference over here. And so all the potential differences are the same for a parallel combination. So the first property is the total potential difference equals the potential difference across capacitor 1 equals potential difference across capacitor 2 equals potential difference across capacitor 3. Okay, so for a parallel combination, all the potential differences are the same. The reason is these are all conducting wires. There is no potential difference across a conducting wire. Okay, how about for charges? Okay, this positive terminal of the battery, what is it doing? You can take electrons. Where does it take the electrons from? It takes it from all of them. Okay, it takes electrons from all these capacitors, right? So the total charge is going to be the sum of the charges of the individual capacitors. Okay, so the second property is the total charge equals the sum of the charges in the capacitors. Okay, so these are the two defining properties of this kind of combination. All the potential differences across the capacitors are equal, and they're equal to the total potential difference. But the charges, to get the total charge in the circuit, you have to add the charges accumulated by each capacitor. Okay, now I'm going to replace this using the formula Q equals capacitance times potential difference. Okay, this one is CEQ times delta V, this is C1 times delta V, and so on. Okay, so let me write over here. I'm going to use the second equation. I have this one, Q equals Q1 plus Q2 plus Q3. Okay, but this one equals CEQ times the potential difference. This is C1 times delta V1. This is C2 times delta V2. This is C3 times delta V3. Okay, but remember, all these potential differences are equal, right? So you can take off the subscripts over here. All the potential differences are equal. They're equal. And see, delta V cancels out from this equation. So you get a formula for the equivalent capacitance. Okay, it's simply the sum of the combinations of the capacitors. Okay, so for a parallel combination, the equivalent capacitance, that is a single capacitor that can replace the combination, is simply the sum of the individual capacitors. Okay, uh, maybe let's consider an example. Suppose let's say we have this battery, maybe 6 volt, is connected to the following two capacitors. Okay, and then it's connected like this. All right, let's say maybe this is C2 equals 2 farad, maybe this is C4 equals 4 farad. Okay, the question is to find the potential differences in charges across the capacitors. Okay, find the potential differences and charges across the capacitors. Charges across the capacitors. Okay. Now, can you tell me what the potential differences are? What do you think is the potential difference across this one and this one? You remember the first property of this kind of combination? No? We said all the potential differences are the same. You see that? So our total potential difference in this case is 6 volts. So all the other potential difference should also be 6 volts. Okay. So for power combination, all the potential differences are the same. So for the potential differences, what we have is delta V2, the potential difference across this one, equals delta V4, equals delta V, but delta V is this one, 6 volt. Delta V equals 6 volt. So they're all 6 volts. Okay, all the potential differences are equal. Now we can calculate the charges because Q2, the charge across capacitor 2 is C2 times delta V2. Okay, so this is 2. The charge is same for all of them, 6, which is 12 coulomb. Okay, how about Q4? It is C4 times delta V4, right? That is 4 times the potential difference, which is 6. So you've got 24 coulomb. Okay. Now, what's the total charge? The total charge is Q2 plus Q4. Okay. That is 12 plus 24. That is 36 coulomb. Okay. Let's check using the following formula. Total charge equals CEQ times total potential difference. Okay, what is CEQ? C equivalent capacitance in this case is simply C2 plus C4. Okay, that is 2 plus 4, that is 6 farad, right? So this will be 6 farad times 6 volt, you get 36 coulomb. Okay, so in either case, you get the same charge over here. Okay, so that is an example of a parallel combination. Now we're going to look at the second type of combination, which is series combination. Okay, let's look at the series combination. This is combination in a single line. Okay, this is combination in a single line. Combination in a single line. In a single line. So if you have combination like this is said to be series. Okay, these capacitors are said to be connected in series. All right, once again, our goal is to get a formula for the equivalent capacitance, a single capacitor that can replace this combination. Okay, so first let's look at the properties of this kind of combination. All right, suppose I have the following. Let's say this is a battery connected to the following 3 capacitors connected in series like this. Okay, let's say these are C1, C2, C3, and then let's say the potential difference of the battery is delta V. Okay, now first let's look at the charges. What do you think the battery would do? Remember, the space between the plates of the capacitor is insulator, so charges cannot cross these insulators over here. Okay, so what this battery going to do is going to take charges from here. It cannot take charge from here. So it's going to take electrons from this side and again put them on this side. Okay, so this we're going to take, this is going to be positive charge, this is going to be negative charge over here. But what it's doing is taking electrons from this one and putting them over here. Nothing is happening inside. Do you see that? Because it's an insulator. This battery is taking charges from here and putting them on this plate over here. But then what happens? You see this charge over here? We have negative charge over here. You've got positive charge over here. This negative charge over here, they push the electrons over here. So those electrons, they go over here, and then you got positive charge over here. The same thing over here. We're going to have negative charge over here, plus charge over here. So, but this charge over here are not real charges. They are induced charges. The only real charges are this charge over here, the charges outside, okay? So all these capacitors are going to have the same amount of charge, okay? So the first property is the total charge accumulated by all the capacitors, they're all equal, equals Q1 plus, Q2. Q2 equals Q3. Okay, that's one of the properties of a series combination. If capacitors are connected in series, then all of them contain the same amount of charge, and that charge equals to the total charge in the system or in the combination. All right. Now let's look at the second property, that is with potential differences. Now remember, potential difference is related with work. Remember, potential difference is this is change in energy divided by charge, but this is negative of work divided by charge, okay? So potential difference is proportional to work. So if you want to take a charge from here to here, you have to do work against the electrical force to go from here to here. You have to do work to go from here to here. You have to do work from here to here. In other words, the total potential difference or the total work is the sum of the work you have to do to cross each capacitor. Okay, so the total potential difference from here to here is the sum of the potential difference from here to here, from here to here, and from here to here. Okay, so the conclusion is the total potential difference is the sum of the potential differences across the capacitors. Okay, so you see they change. In the case of parallel, the potential differences were the same, but in this case, the charges are the same. That's what makes them different. That's the difference between both kinds of combinations. All right, now I'm going to use this equation, and potential difference is charge divided by capacitance, right? So this is for the combinations. So it's going to be total charge divided by equivalent capacitance, okay? But delta V1 is Q1, but all the charges are equal. It's going to be Q over C1. This is Q2 over C2, but all the charges are equal. Q over C2 plus Q over C3. Okay, you see that the charges cancel out. So you get the following equation. 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3, and there are some more, the same pattern continues. Okay, so that's how how we calculate the equivalent capacitance of a group of capacitors connected in series. That is, the inverse of the equivalent capacitance is the sum of the inverses of the capacitances. Or if you want, you can write it like this. Maybe that's easier to use on a calculator. You take the inverse, and then you've got 1 over C1 plus 1 over C2 plus 1 over C3, and so on. And then you take the power of -1. Okay? Maybe this formula will be easier to put in a calculator. But if you have only two capacitances, we can find an easier formula. I know this formula is cumbersome, but if there are only two capacitors, you can get a nice formula, a nice easy formula. So let's simplify it for two capacitors, okay? For two capacitors. For two capacitors. So 1 over CEQ equals 1 over C1 plus 1 over C2, okay? So you take the LCM, which is C1, C2, and you get C1 plus C2 over here. And then you have to take the inverse. This is the inverse of the equivalent capacitance. And you get the equivalent capacitance simply product over sum, okay? But this is true only for two capacitors. If you've got three capacitors, you cannot say C1, C3 equals C1 plus C2 plus C3. You can do that. This is only for two capacitors, okay? So this formula gives you the equivalent capacitance of two capacitors, but if you get more than two capacitors, you got to use this general formula over here to find the equivalent capacitance. All right. Maybe let's consider an example. Let's say we have the same thing over here. This is 6 volt over here, but this time they're connected in series like this. Okay. Let's say this is 2 farad. The C4 is 4 farad. By the way, I don't think I mentioned the unit of capacitance is called farad, after Michael Faraday. Okay, so the question is find the potential differences in charges across these capacitors. Okay, the question is find the potential differences or the voltages and charges across on the capacitors. Okay, that's the question. So how do you think we should proceed? I think in this case, the easiest thing would be first to simplify the circuit. We can change this into a circuit with a single capacitor by calculating the equivalent capacitance, okay? So let me calculate the equivalent capacitance of these two, the combination of these two. This is series combination, so it's going to be product over sum. That is 2 times 4 over 2 plus 4, right? So that is 8 over 6 or 4 over 3, okay? Now I have simplified the circuit as the following. I've got a 6-volt battery. This is equivalent to connecting this to this CEQ equals 4/3 farad. Okay, I have simplified the circuit. All right, now I can calculate the charge. Okay, that's the total charge. Q equals CEQ times delta V, right? Total potential difference times the equivalent capacitance of those two capacitors. So that is 4/3 for the equivalent capacitance and then 6 for the potential difference. You get 8 coulomb. Okay, so the charge accumulated by the equivalent capacitance now is 8 coulomb. Okay, can you tell me the charge accumulated by these two capacitors? They're in series. Huh? If they're in series, remember this formula over here? If they're in series, all the charges are equal. Okay? So the charge accumulated by the combination is the same as the charge accumulated by the individual charges. Okay? So I just obtained the charge obtained by the combination. Okay? But that equals Q2, that equals Q4, which is 8 coulomb. Okay, so all the charges are equal because they're connected in series. All right, now I can do the potential differences. Delta V2 is Q2 over C2. That will be 8 divided by 2, that is 4 coulomb. And then delta V4 would be Q4 divided by C4. That will be 8 divided by 4. That will be 2 coulomb. Okay. So if you've got a circuit with series combination, the easiest thing to do is to simplify the circuit. You first find the single capacitor that represents the combination. From that, you can find the total charge, and then you go backwards. The combination and all the capacitors will have the same charge. Okay? Now, let's look at an example. Suppose you charge a capacitor. Let's say it's maybe 8 volt over here, and you got a capacitor. Let's say this is maybe a 4 farad capacitor. Let's say it's a 4 farad capacitor. So what's the charge accumulated by this capacitor? How do you calculate? We have potential difference. Delta V is 8 volts. And we have the capacitance is 4 farad. What's the charge? The charge is C times delta V. Okay? That is C is 4, delta V is 8. So you've got 32 coulomb, right? Now suppose we disconnect it from the circuit. Okay, so what we have is we have a capacitor. I took it out from the circuit. Okay, I'll break this connection over here. So what I have is I have 4 farad capacitor with a charge of 32 coulomb. Okay, so I've got 32 coulomb over here, and then of course the capacitance is 4 farad. Okay, I've got 4 farad over here. Now I have this charge capacitor, and I connect it to another capacitor. Let's say maybe a 2 farad capacitor. 2 farad capacitor. Okay. So the question is, how much charge will be transferred from this capacitor to this capacitor? You see, this is already charged with 32 coulombs. We have charges over here. This is neutral. Now I'm taking this capacitor and connecting it to this capacitor. Obviously, some of the charges are going to flow from here to here, but not all of them. Okay. Let's look at an analogy. Suppose you have water in this tube. Okay, you fill this water all the way over here. All right, and then after you fill it, you connect it to another tube over here. So of course, some of the water will go over here, but until when does the water flows from this to this tube over here?
Until they have equal amount of water.
Until not equal, until they're the same level. You see, this water will flow from here to here until both of them will have the same level. Okay, the same thing over here. What's going to happen is the charge will flow from here to here until both of them have the same potential difference. Okay, that's what's going to happen. So the question is, calculate the amount of charge transferred from the 4 farad to the 2 farad capacitor. Okay, that's the question. Okay, now let Q be the charge transferred. Okay, let me say let Q be the charge transferred. Okay, so that means this will have a charge of Q, this will have a charge of 32 minus Q. Okay, if a charge of Q is transferred, this is going to have a charge of Q, this will have 32 minus Q. Okay, now charges will be transferred until both capacitors have the same potential differences. Okay, so the main thing over here is charges will be transferred. Charges will be transferred until both of them have the same potential difference. Both of them have the same potential difference. Okay, so what does that mean? Let's calculate the potential difference of each. This one has a charge of 32 minus Q, so the potential difference is charge divided by capacitance, right? So this will be this charge divided by 4, will be the potential difference of the first. So this implies 32 minus Q divided by 4. This is the potential difference of this capacitor by the time all of them have the same potential difference, okay? And this will just be Q over 2. This will be Q over 2. Its capacitance is 2, its charge is Q, so its potential difference charge divided by its capacitance, okay? So you just solve this equation to find, so you've got 32 minus Q, okay? That is 2Q, okay? You take for the other side, you get 2Q, and then you've got 32 equals 3Q, and so the charge transferred is 32 over 3 coulomb, okay? So the main thing is charge should be transferred from one of the capacitors to the other until both of them have the same potential differences. Okay, now we're going to look at circuits where you have both parallel and series combination. Okay, so let's look at parallel series combinations. Parallel series combinations. Series combinations. Okay. Now suppose we have the following. Maybe I'll put over here to the other side. Let's say each capacitor is 2 farad capacitor. Each capacitor, let's say, is a 2 farad capacitor. And then we have the following combination. Let's say we have this capacitor over here, and then you have parallel combination over here like this, and then you've got another series combination over here. Maybe you have 3 capacitors over here like this, and maybe you have another capacitor over here. The question is, find the equivalent capacitance of this capacitor. The question is, find the equivalent capacitance of the combination. Equivalent capacitance. Equivalent capacitance of the combination. Okay, how do you think we should go about it? So we're going to combine the parallel using the parallel formula, and then the series using the series formula. That's what I'm going to do, okay? So first what I'm going to do is, you see these are in parallel, I'm going to add them using the parallel formula, which is the sum, right? That is 2 plus 2. For parallel, you just add them, right? So this is equivalent to a capacitor of capacitance 4, okay? And then I can add this too, they're all in series, okay? But they're in series, so it's going to be, you take 1 over 2 plus 1 over 2 plus 1 over 2, and then you take the inverse, okay? That's how you do it. This is, so that's 3 over 2, inverse, that's going to be 2 over 3. So these are equivalent to 2 over 3 farad, okay? So I've got a new simplification over here. I've got a new combination over here. I'm going to replace this by 4 farad. Okay, this over here. I still have this 2 farad capacitor over here. I replaced all these three by a single one, which is 2/3 farad. Okay, so I've got the following now. And I've got another 2 farad capacitor over here. What do I do next? Do you see any series parallel? You see these two are in series, right? So that's product over sum. So I can add them like 2 times 4 over 2 plus 4, which is 8/6 or 4/3. Okay? So now I have another simplification of this one. I'm going to replace by one capacitor, which is 4/3 now. And then I have another one over here, which is 2/3. And I have another one over here, which is still 2. Okay? This 2, this is 2. Now I've got two capacitors in parallel, right? How to add capacitors in parallel?
Just add them.
Just add them, yeah. So this one over here is going to be 2/3 plus 4/3, which is 6/3 or 2. Okay. Now I have the following. I've got a 2 over here. I've got a 2 over here. I've got a 2 over here. Okay. And they're in series and series over here. Okay. And that's going to be, you take the inverses and then the power of -1. Okay. That is that is 3/2, and you get 2/3. Okay. So the equivalent capacitance of all this combination is just this one. Okay. If you replace this entire combination with this one, nothing will change. All right. Now let's look at an example in a circuit. Suppose I have the following example. Suppose I have the following battery. Let's say it's once again is 6 volt. And then I've got, maybe I have 2 farad over here. And then I have maybe 4 farad over here, maybe 6 farad over here. Okay. So the question is, find the voltages and charges across each capacitor. Okay. Find the voltages or potential differences, voltages and charges across each capacitor. Across each capacitor. Okay. So how do you proceed? Well, first we're going to simplify. Okay. You see these two are in parallel, right? I can combine them. And since they're in parallel, how do I find the equivalent capacitance? Simply add them, right? For power combination. So I can combine these two and simplify the circuit, okay? That is 6 plus 4, 10. So I can simplify this. This one over here is 6 plus 4, which is 10 farad, okay? So with that, let me just call this C2, this one C6, and this one maybe C4, okay? All right, so I have the following now. I've got my battery, which is 6 volt, that's my delta V. And then I've got 2 farad over here, C2 equals 2. Now I have replaced this with this combination of 6 and 4, which is 10 farad. Okay? So you see, now I have a situation that we already solved over here. You remember we solved a series circuit over here? Anyway, somewhere. Anyway. So what do? We can further simplify it. We can replace it by a single capacitor, right? And these are in series, so it's going to be product over sum. Okay, so when I combine these two, it is product over sum. 2 times 10 divided by 2 plus 10. Okay, that is 20 over 12, or by 2, or by 4, 5 by 4, 3. Okay, so this is 5, 3. The equivalent capacitance is 5/3 farad. Okay, so this is equivalent to the following. We have now the following, but now I have a single capacitor, which is the equivalent capacitance CEQ equals 5/3 farad, okay? And it's 6 volts. Now I can calculate the total charge, right? Because I have only one capacitor, and that total charge is equivalent capacitance times total potential difference, okay? So the total charge is CEQ times delta V, which is 5 over 3 times 6. You see 2, that's 10 coulomb. Okay, so the total charge is 10 coulomb. But remember, this is a series combination of these two. So what do you think are the charges in here? They're in series, right? So they're in series, the charges are the same. Remember, in parallel, the volts are the same. In series, the charge are the same. So this charge is the same as these two charges. All right? So I can say Q2, and Q64, they are equal to Q, and that equals 10 coulomb. Okay? From this, I find these charges very easily. All right? So now for this capacitor over here, I know the charge, I know the capacitance. So I can do the potential difference, okay? So let me see delta V2. Delta V2 is Q2 over C2, okay? So that's 10 divided by 2 farad, that's 5 volts, okay? So the potential across this capacitor is 5 volts. Now, can you tell me the potential difference across this one? You see, the total potential difference is the sum of the potential differences over here, right? So the total is 6. This one is 5. What do you think is this one?
1.
1. Yeah. So it should be 1 volt. All right. But if you want, also you can do like this. You can find the potential difference of this, which is 10 divided by 10, which is 1 volt. And then these two are going to have the same potential difference. Okay. So, but let me use this one over here. Delta V2 plus delta V64 equals total potential difference, right? So just calculate this to be 5 volt over here. So this one over here equals 6 volt. So this one over here is 1 volt. Okay, so this is it. Now, the potential difference across this one, which is a combination of these two, is 1 volt. Okay, now can you tell me? Now let's go back. If the potential difference across this one is 1 volt, what do you think is the potential differences across these two capacitors? They're in parallel. In parallel, what is the same? Charge or potential difference? In parallel, potential difference are the same, okay? So if this is 1 volt, this also should be 1 volt, okay? For a parallel combination, all the potential differences are the same. So delta V64 equals delta V4 equals delta V6 equals 1 volt because they are in parallel, okay? They all have the same potential differences. Now I can find the charges in 4 and 6. Q4 is C4 times delta V4, right? So that is 4 times 1, you get 4 coulomb. And then Q6 is C6 times delta V6, which is 6 times 1, you get 6 coulomb. Okay, so that's it. We have the charges and potential differences for each capacitor. All right. Do you have any questions so far? All right, let's continue. Next, we're going to look at energy stored by a capacitor. Okay, energy stored by a capacitor. Once again, this energy is equal to the amount of work that has to be done to charge the capacitor, okay? Suppose you have, let's say this capacitor over here, and you're connecting it to a battery like this, okay? Now the battery is going to do work to charge this capacitor, right? So the amount of work that the battery has to do to charge this capacitor is the amount of energy that is stored by by the capacitor. Okay, so this charge, this battery is going to push charges uh, through potential difference. But remember, potential difference and charge are proportional. The charge, let's say you have a graph over here. You have a zero charge over here. As the charge increases, let's say the charge over here, the potential difference over here. Now remember, charge and potential difference are proportional because you've got Q equals C times delta V. Or you can say, in this case, maybe delta V equals 1 over C times Q. Okay, so what happens? As the charge is being accumulating, the potential difference increases proportionally. Okay, so the graph of potential difference versus charge as the capacitor charges is linear. The graph of potential difference versus charge is linear. Okay, as the charges keep going, the potential difference also increases proportionally. So this gives you the graph of potential difference versus charge as the capacitor is charged. Okay, so let's look at the amount of work the battery has to do when it's transferring this charge dq. Okay, by the time the potential difference is delta V over here. Okay, so remember, what's the relationship between energy and potential difference? Potential difference is defined to be change in energy per unit charge. Okay, this is the definition of potential difference. If you delta V equals delta U divided by Q, right? Or delta U equals Q times delta V. All right. So the amount of energy that the battery has to do to transfer this charge dq through a potential difference dV is simply du equals uh, the potential difference delta V times dq. Okay, that's the amount of work the battery has to do to put this energy on the capacitor. Okay, and if you want to find the total, you just add up all triangles over here. Okay, or you just integrate this one. Okay, so you can say that the integral of du would be the integral of this one. You have the potential difference delta V, and you have charge dq over here. All right, but we can express delta V in terms of charge using this formula over here. Okay, so the delta V is the charge, maybe means q over here, q over c, right? This potential difference over here is charge by capacitance. Okay, so I can do this integral like this. I've got q over c times dq. And the charge was initially was 0, but then let's say it increases to an amount q. Okay, so you get 1 over c, and this is q squared going from 0 to total charge. Okay, what am I forgetting? Delta v is q over c. Okay, so the energy is, so you've got u equals q squared. There's a half over here, I'm sorry. This is what I forgot. The integral of q dq is half of q squared, right? So I've got q squared over 2c. All right? So this is the amount of energy, amount of work the battery has to do to increase the charge from 0 to q. Okay? So this half comes from the integral. Or this is, you see, it's a triangle. So this area will be half of base times height. All right. So this would be the formula for the energy stored by a capacitor of charge Q and capacitance C. Let me put it in box over here. So this is our formula. U equals Q squared divided by 2C. Okay. So this is energy stored by a capacitor of charge Q and capacitance C. This is energy stored by a capacitor of charge Q and potential difference, capacitance C. Capacitance C. Now let's try to write this in terms of potential difference. Okay, so we know that Q equals C times delta V, right? C times delta V. So if I put C times delta V, what do I get? U equals C times delta V squared divided by 2C. Okay, so that is C squared delta V squared over 2C. Okay, so I get U equals 1/2 of C delta V squared, okay? So that's another formula you can use in terms of capacitance and potential difference. Or if you want, you can substitute for C. C is Q over delta V, right? So if you do that, you have Q squared divided by, there is, well, there's 2 over here, and then this is Q over delta V, right? So you just have delta V goes up, you get half of Q times delta V. So that's another formula you can use. Okay, U equals half, this energy equals half of charge times potential difference. So depending on what you have, you can use either these formulas to calculate the energy stored by a capacitor. All right. Okay. Now we're going to talk about energy density of a parallel plate capacitor. Energy density, energy density of a parallel plate capacitor. Okay, what is energy density? It's energy divided by the volume. Okay, so let's say you have this capacitor over here. Let's say the area of this one is A. Okay, and let's say the separation is D, this one over here D. So the volume between these plates is going to be A times D. Okay, and the energy density is going to be the energy. Let me use this symbol for energy density. Is going to be the energy, which is U, divided by the volume, which is area, times D. Okay, so that's what we're going to calculate. We know the total, we have formula for the total energy contained between the plates of the capacitor. We divide that by the volume, we get energy density. Now, we're obtaining this formula for a very special case, but the formula is very important later when we discuss electromagnetism. It actually applies in every situation. Okay, we're driving for a special situation over here, but it's actually applicable for any situation. Okay, so now let me use the following formula for U. Okay, maybe let's use this one over here. Half C delta V squared. Okay, so this is energy, half of capacitance times delta V squared. Okay, now what does C equal to for a power plate capacitor? Do you remember? That equals epsilon times area divided by separation. Do you remember that? For a power plate capacitor, the C parallel, the capacitance is this permittivity, electrical permittivity of vacuum. This is area of the place, the separation between the plates. All right. How about delta V? Delta V for a constant electric field. As if in the experiment, if you've got 2 parallel plates, the electric field is uniform, a constant. And so you see this equals E, well, I'll say over here, times this over here like this. But if E is a constant, you take the E, and the integral of dx will simply be the separation in the 2 places d. So this is E times d. All right. The potential difference is simply electric field times distance because the electric field is a constant. All right. So now let me go back to my formula for the energy or the energy density. Energy density, okay, that is U divided by the volume, A times D, okay? And then for this one, we have half C delta V squared divided by AD, okay? So let's put in what we know. We have half C is epsilon area divided by D, okay? Delta V is electric field times distance squared divided by A times D. That's what we have, okay? Now, let's simplify this one. So that's what we have. Half. At the top, we have epsilon A E squared D squared. At the bottom, we have A D squared. Do you see that? So you see, this cancels out. The area cancels out. You get this formula for the energy density. Half epsilon energy electric field squared. So at any point where the electric field is E, this is energy density. This is a very general formula. Okay? At any point where the electric field is E, the energy density or the electrical energy density per unit volume is given by this formula. Okay? So this formula is a very general formula. We're going to see later when we study electromagnetism. All right? Okay. So finally, we're going to talk about dielectrics. So far, we've been assuming that the space between the two conductors is air, but now we're going to put an arbitrary insulator between the two conductors. Okay, that's called dielectrics. So we're going to look at capacitors with dielectrics, capacitors with dielectrics. A dielectric is an insulator between the conductors of a capacitor, what we call a dielectric. This is an insulator between the conductors of a capacitor, conductors of a capacitor. Okay, so far we've been dealing with vacuum or air, but now we're going to put an arbitrary insulator between the conductors of the capacitor. Okay, so let's say we have the following now. Let's say these are the conductors of our capacitor. Okay, and we put insulator. Insulator is made of molecules, right? So let's say we have these molecules over here like this, between these two, something like this. I don't have to do all of that. Okay, suppose we have these molecules of the insulator. Okay, now we charge the capacitor. What happens? Let's say we charge this with positive and we charge this with a negative charge. But remember, these molecules have charges. Okay, they have electrons. What's going to happen to them? This positive charge over here is going to attract the electrons towards it, right? So this end of the molecule is going to be negative. The other end is going to be positive. You see, because they will be attracted by this positive charge, and the same thing on this side. Okay. So what's going to happen is you're going to have separation of charges in these molecules. So you have a new kind of electric field. You see. Now the electric field, the outside electric field between these two, remember electric field goes from positive towards negative, right? We have this electric field between these two charges over here. But now we have another electric field over here. You see, this positive charge attracts the electrons, and then this end becomes negative, this end becomes positive, right? So you have another electric field that goes in the opposite direction. You see, all these molecules will have an electric field that goes in the opposite direction. So you're going to have negative over here plus, you got electric that goes over here, and so on. So all these molecules will have an electric field that goes the opposite direction. So what do you think happens to the net electric field? Increase or decrease? You have this original electric field E naught, but then you have other electric field over here in these molecules. Because of this charge over here, the molecule, the charges of the molecule have been displaced. Okay, so you got positive over here, so the negative will come over here, the positive will come over here. That will produce this electric field over here. So you got electric field in this direction. Are these electric fields opposing or helping this field? You see, the direction of the electric fields is this way. Can you see it? But the outside electric field is this way. So do you think it's going to decrease or increase the electric field?
Decrease.
Decrease, because this electric field is opposing this electric field. Okay, so the new electric field is less than the original electric field. Okay, so what this tells you is the presence of a dielectric, decreases the electric field because of polarization, decreases the electric field. Okay, so that's what we have. This one over here is electric field without dielectric or with vacuum. This is electric field with vacuum or air. Okay, and this one over here is electric field with a dielectric electric field or the insulator with a dielectric. Okay, and we just conclude that the electric field with the dielectric is smaller than the electric field with vacuum. Okay, now we define the dielectric constant of the insulator. The dielectric constant is defined with the ratio between the original electric field and the electric with the dielectric. Okay, so dielectric constant, let's say the ratio between E naught and E is defined to be the dielectric constant of the construct of the insulator is defined to be the dielectric constant of the insulator or of the dielectric of the insulator. All right. So this is a definition of the dielectric constant. It is the original electric field, electric with vacuum, divided by the electric field with dielectric. Okay. So this is a definition of dielectric constant of the insulator. And the electric field decreases with the presence of dielectric. Okay, so we have this formula, or maybe it's better write this way. This is E naught divided by K. Okay, so what does it tell you about the value of the dielectric constant? Is it smaller or bigger than 1? Remember, this is smaller than the original field, right? So do you think this constant is bigger or smaller than 1?
Larger.
Yeah, this is smaller. So dielectric constant is 1 for vacuum and bigger than 1 for any other dielectric. Okay, so dielectric constant is always greater or equal to 1. So this constant over here is greater or equal to 1. It is 1 for vacuum or air approximately for vacuum, or you can say air approximately. All right, so the dielectric constant is always a number bigger or equal to 1. It's 1 for vacuum, but it's bigger than 1 for any other insulator. Okay, so we've seen that the electric field decreases when a dielectric is inserted between the conductors. How about potential differences? Okay, let's compare the potential difference before delta V naught is going to be electric field before times distance, right? How about the potential difference after? It's going to be the electric field after times distance, right? So you find the ratio, what do you get? Delta V naught over delta V equals E naught over E. What does this equal to? No, this is E over here. This equals the dielectric constant, you see? Kappa is E naught over E, okay? So what we have is we have this dielectric constant over here. This equals the dielectric constant. So we have a formula for the new potential difference. Potential difference equals the original potential difference divided by the dielectric constant. So do you think the potential difference increases or decreases with the dielectric? Remember, this is bigger than 1. Does it decrease or increase? This is
Decrease.
decrease. This is original potential difference, okay? And this is bigger than 1. So the new potential difference is smaller than the original potential difference, okay? So the conclusion is potential difference decreases with the dielectric, okay? Potential difference decreases with a dielectric, okay? How about for capacitance? Let's look at what happens capacitance. Now, remember, Q is the charge outside, so there is no change to this charge. Whether there is dielectric or there is no dielectric, the charge remains the same, okay? So the charge before and the charge after are equal, okay? So we have the following conclusion. Q naught equals Q. Charge doesn't change. We're talking about the charge in the conductors. That is not affected by the presence of an insulator between the conductors. Okay, so now let's look at the capacitances. This is before a dielectric or with vacuum. Okay, so by definition, that's charge divided by the original potential difference, right? All right. So this is okay. Q naught, it doesn't change. How about delta V naught? Delta V naught is delta V. Well, let me do. Okay, let me start over here and then let me do C. C is Q divided by delta V, right? How about delta V? Delta V is delta V naught over K, okay? So you've got, this is Q, and then you've got delta V naught over kappa, the dielectric constant, okay? So you've got kappa and then Q over delta V naught, okay? But this one is equal to Q naught because the charge doesn't change. So you've got kappa Q naught over C naught, okay? This is the delta V naught. But this is the original capacitance without dielectric, right? So you've got the capacitance after the dielectric is dielectric constant times the capacitance before the dielectric. Okay? So what does it tell you about capacitance? Does dielectric increase or decrease capacitance?
It increases.
Increases. So you see only capacitance increases when you put a dielectric between it. So if you want to increase the capacitance or the amount of charge it can hold per unit volt, what you do is you put an insulator between two capacitors. Dielectric helps the capacitor to store more charges. Okay, that's what capacitance measures. Capacitance measures the amount of charge the capacitor can store per unit volt. Okay, so by putting a dielectric between the conductors of a capacitor, you have the capacitor to store more charges. So the conclusion is capacitance increases with a dielectric. Capacitance increases with a dielectric. Okay, so let me summarize what I've done so far. The charges doesn't change, Q naught. Okay, the final electric field is the original divided by the electric constant. The final potential difference is the original potential difference divided by the electric constant, but the capacitance increases. That's the only difference. Okay, so these are the four conclusions from the effects of a dielectric. The electric field decreases, the potential difference decreases, but the capacitance increases. Okay, so maybe let's look at an example. Let's look at some very popular examples. Um, Suppose I have the following situation. I have this capacitor, okay? And then half of it is air and half of it is uh, a dielectric with, let's say, dielectric constant kappa, okay? So this one is air or vacuum. This one is dielectric of constant kappa. This kappa over here. Okay, so the question is to find the capacitance of this capacitor. Okay, this is a parallel plate capacitor. Okay, I should say parallel plate capacitor. Parallel plate capacitor. So what do you have over here? You charge this plate outside. Let's say it's positive, and this end is negative over here. Okay, so you have two capacitors. Well, if you want to find the combination, then you have to treat them as two capacitors. Okay, you've got this one, a capacitor with vacuum, and over here you've got a capacitor with dielectric. Okay, do you think these two capacitors are in parallel or in series?
They'd be parallel, wouldn't they?
Parallel. If the positive is connected with positive, it's parallel. Okay, negative, negative, that's parallel. In a series, you've got positive, plus, positive, minus, plus. It alternates, okay? But in this case, you've got positive connects positive, negative connects negative. So they are in parallel, okay? So let's say this is the area A, and this is separation D, okay? So we have two capacitors, this capacitor and this capacitor, and they're in parallel. So we're gonna add them, right? So the total equivalent capacitance of this one is, let's say, C of the one with air, they're in parallel, so I just have to add them, okay? C with dielectric, okay? What is the capacitance of this one? Remember, this is a power plate capacitor. It is epsilon, but the area is now half of the area of the plate, okay? So I'm going to put A over 2 over here. It's half of the area over here, all right? And then divide by the separation D, okay? That's this one. How about this one? This is kappa times the capacitance in air, okay? The capacitance increase when you put dielectric, so I'm going to just multiply this, and then have the same thing. Epsilon, half of the area, okay? And then divide by D, D is the same, all right? So what do I get? You can factor out epsilon A over 2D. You can factor from both of them, and you get 1 plus kappa, okay? So this would be the capacitance of this combination, all right? Now let's move it around. Instead of filling it this way, let's put it halfway like this. So I'm going to put dielectric over here, and then air over here, okay? And then you got this charge over here like this. Again, the same thing. This is the area, this is the distance, okay? Now, do you think these two capacitors are in series or in parallel?
Series.
Series, these are in series, okay? You see plus, minus, plus, okay. So we're gonna use product over sum to add them, okay? So the equivalent capacitance in this case is the capacitance of the air one times the dielectric one divided by the sum. You've got air plus C dielectric. That's how we're gonna add them, okay? So what is the air one? Let's look over here. This is the air one. It has area A, but separation is D over 2. Do you see that? We have area is A, but the separation is half of D, okay? So the air one is epsilon A, but this one is D over 2, okay? So this is the air one. How about this one over here? It's the same thing, but this will be multiplied by its dielectric constant, kappa, okay? It will be kappa times the capacitance with air, okay? So this one is going to be kappa, and then you have epsilon, the area is A, but the separation is half of D, all right? So you've got this one divided by D over 2, okay? And then at the bottom, we just have the sum. We have epsilon A over D over 2 plus kappa epsilon A over D over 2. Do you see that? Now we're going to factor out this epsilon over D over 2. Let's factor this expression, it's common to all of them, okay? So we have, well, actually, this is going to be, we have two of them, so it's not factor, will be A D over 2. This is going to be squared, okay? All right, so I've got kappa left over here, okay? How about the bottom? I factor out epsilon A over D over 2. What do I get? I have 1 over here. I've got kappa over here. Do you see that? You see? And then one of this cancels with this one. So you've got the following is epsilon A over D over 2, or 2 over D, okay? And then what do you have over there? We just have kappa at the bottom, and then 1 plus kappa at the bottom, okay? So this would be the dielectric, the capacitance of this combination over here.
Could you shift the pad just a little bit to the right?
Oh, I'm sorry. Was it like that for a long time?
No. It only just got to where we couldn't see just now.
Okay, all right, okay. So maybe do you want me to repeat this one then? This one? Was it off when
We were able to see until just the last little bit that you wrote, just
Oh, okay.
the most recent page.
Okay, so all I did is I put dielectric over here, and insulator over here. This one is air over here. So you can look at this as two capacitors, one with air and one with dielectric, right? And they're in series, so you got to use product over sum to add them together, right? So this is the capacitance of the one with air. This one, the capacitance of one with dielectric. The only difference is for the dielectric, you multiply by kappa, right? And then you add them over here. And then I just factor out this. And then eventually I got this expression over here. All right. So do you have any questions so far? No? All right then. On Tuesday, we're going to work on practice quizzes of this chapter. All right. I'll see you on Tuesday. Bye-bye.
Thank you, Professor.
You too. Thank you. Bye-bye.
Have a good weekend, everyone.
You too, Dr. Brewer.
Thank you.